John Rudge, the fine individual who's brought you all here. I promised I'd give a really long introduction. Look at that. Okay, all right. Everybody, John Rudge.
Thank you. Thank you, Dave. Thank you. Right, so what I'd like to do this morning, so for this first talk today, is just to give an overview of the two-phase flow equations that have been used to look at melt transport in the mantle, I suppose used by the community for more than 30 years now. I know a number of members of this audience have worked with these equations much longer than I have and know them better than I do. I do apologize for going over a lot of these things, but I know a number of people in this room are unfamiliar with this field. For those of you who do know all this stuff, please feel free to interrupt, heckle, let me know when I'm saying things which aren't quite right, and also those who aren't familiar with these equations, please do interrupt if anything's not clear. I thought I'd begin with this nice quote from George Batchelor, who was a fluid dynamicist here in well, I suppose over in Dampt. He had these wonderful remarks to make about two-phase flow, talking about these things for those who like their research problems to be reasonably well defined physically and formulatable in mathematical terms. This is probably not a suitable field. Now obviously this is a bit of a problem for this whole program of the Isaac Newton Institute. We really want to have some formulate in mathematical terms models for melt transport. I disagree, we can't do things like this, but I do very much agree with his second remark. A taste for pioneering and preparedness to live with confusion are more appropriate qualifications. Now, there are a number of aspects of the theory that still confuse me now, and I will point out some of my confusions as we're going along, and I'm hoping some members of the audience here can help relieve some of my confusions. And I suppose the last remark is a good remark for encouraging mathematicians to really look at this theory and think about the kind of deeper underpinnings of the theory, not just quick answers to practical questions. Okay, so the talk's going to be in three parts. So I'm going to begin just going over, I suppose, the basic conservation laws for two-phase flow, conservation laws for mass, momentum, and energy, and talking about the various choices one has to make along the way to get a closed set of equations. Then I'm just going to go over some of the kind of simplest physics that comes out of these problems. Particularly I want to talk about what happens in these problems of instantaneous compaction, talking about I suppose the natural length scale in these equations, which is this thing called the compaction length, the natural velocity, the percolation velocity. Talk about some very simple instantaneous compaction problems. And then I want to go on to do just a brief overview of just a very simple situation of mantle melting, which is a 1D steady state melting column. So those are the things I want to touch upon in this talk. So we want to describe the partially molten regions of the mantle, and mantle rock is made of is a polycrystalline material made of crystals, and when it is partially molten, it's thought that melt lies along the grain boundaries. So this is just meant to be a schematic picture of a grain with the melt lying here along the grain boundaries, and it's thought that even at very small porosities is thought to form an interconnected network, where that happens depends on the surface energies on the dihedral angle. It's thought to be such that it forms an interconnected network, and that allows the melt to segregate by percolation. So the melt can percolate along the grain boundaries and come to the surface. Now, it's more than just a question of the movement of the melt. The matrix itself, so that when I'm using the word matrix, I'm referring to the solid phase. The matrix itself can also deform. And it can deform by creep mechanisms, by particularly, say, for example, by diffusion creep, that under applied stresses, chemical potential gradients are set up which allow atoms to diffuse either within crystals or along grain boundaries, changing the shape of the grains so we can deform the matrix as well as moving the fluid. So it's definitely it's a two-phase system. So it's a two-phase system where both phases move essentially, and I'm going to talk about two phases being the liquid melt and the solid matrix. So even though we've got a solid here, I'm going to use essentially the laws of fluid dynamics to describe it because it can flow. So now I'm going to build up a continuum model of this process, and this was really done in the 80s by Dan McKenzie and several other workers at the same time, so including Scott and Stevenson and Andrew Fowler. Put together a kind of continuum description of this two-phase system, and it's really the equations we've been using to look at this ever since, with a few extra tweaks, and certainly Dave's going to talk about some of the extra things like surface energy and damage that we can put onto these equations. I'm just going to talk about the basic equations pretty much as they were as of 1984. So, and those equations, the bit that underpins them that we all believe is the conservation laws. You must conserve mass, momentum, and energy. You need to have some statements of equations of states. So, for example, how density depends on temperature. And then the trickier bit, and that's what I want to spend some time just highlighting, is the various choices you have to make of phenomenological laws and constitutive laws for how these things deform, real logical choices. So I'll point those out as I'm going along. Okay, so I'll start with I suppose the most controversial one, the conservation law for mass. So I've written it in two different ways. Let me just start with this first way up here. It's the natural way of writing a statement of conservation of mass. What I'm going to work with here, so these are the two phases. This is conservation of mass, the first equation, conservation of mass for the fluid phase, also the liquid. The second one is conservation of mass for the solid phase. And I'll use F subscripts for the liquid. I'll sometimes use the word fluid, and I'll treat both as fluids really, and S for the solid phase. So there's a quantity in here, phi, which is the volume fraction of melt, the porosity. I'm going to talk about that variable a lot. This phi is the porosity, tells you how much melt you have. The density of the fluid is given by this, rho f, the density of the liquid. And it takes the form of a normal conservation law, partial derivative with respect to time of something plus divergence of flux of something equals, now in here the divergence of flux of something is the volume fraction, the porosity times rho f times the velocity of the fluid. What we've got here, this gamma, we can melt. So it's possible for material to change phases, possible for solid to become liquid and liquid to become solid by melting and freezing. And that's what's captured by this gamma term. There's an interchange of mass between the two phases, potentially. So the solid conservation law looks just like the one for the liquid. We just replace phi by 1 minus phi to get solid fractions. And again, it's the usual rate of change with time of the stuff, divergence of the flux of the stuff. Okay, so that's, I mean, everyone hopefully is happy with that. What I'd like to do, it's convenient for later use to actually rewrite these conservation of mass equations in a slightly different form, and that's in a form for the divergences of the velocity fields. Now, particularly, I'll do it in a slightly, I suppose, asymmetric manner, in that I want to write one equation which is really just a rearranging of this second equation, conservation of mass for the solid, as an equation for the divergence of the solid velocity. If I was and I've broken it up here into three terms. The other one here is some divergence of a mean velocity, which I'll come to in a moment. If you look at the divergence of the solid velocity, which I've broken up into these three terms, I've got 1 over 1 minus phi ds dt of phi. Now, I suppose I haven't told you what ds is here. This, when I'm writing a capital ds, so this is the, I sometimes prefer to work with Lagrangian derivatives, so that's derivative following one of the phases, in particular, usually the solid phase I work with. So this is the partial derivative d dt plus vs dot grad when I write that big D, just in terms of Lagrangian derivative. Derivative following the solid in that case. I write a subscript s. So break this divergence of vs up into these three terms. And all it is just a rewriting of this if you expand out these various derivatives. So one term is 1 over 1 minus phi ds phi dt. The other one is rho s ds 1 over rho s dt. And the other is a melting term, gamma over 1 minus phi rho s. Now, if I had a single phase system, say, if you like, phi equals naught, and there was no melting, then I wouldn't have this term, and I wouldn't have this term, and this you'd recognize as a standard term associated with density variations causing a divergence in the flow. Usually, it's the case that you neglect these kind of terms, and I will throughout, and what I'm going to do here is not worry about the density variations. I'm going to assume, at least for the purposes of this talk, that the two phases remain constant density. Similarly, you've got terms like that down here, and I'm just going to kind of cross all those terms off like that. I'm also going to neglect the density differences between the two phases, except when it's multiplying gravity. That's like a Boussinesque approximation. So I'm going to also not worry about, for the moment, the density differences in there either. That gives you, I suppose, these equations. So I've got rid of these terms which are associated with derivatives of the density, just assume the density is constant and effectively equal in the two phases, but I'm not going to make that assumption later on for momentum. The first equation here tells you about how porosity varies. And there's two bits to it. You can vary porosity associated with the melting, that's gamma over rho s, and you can vary it associated with this term that's associated with a divergence is the velocity field of the solid velocity, and they're the ones associated with compaction. So the idea being that it's possible to expel melt essentially by squeezing the solid and closing the pores, and it's this term that's associated with the compaction. So we've got this one equation here. The other equation here, so just came about because I neglected all these density variations and neglected the density variations associated with melting. This tells me that the divergence of some mean velocity weighted here by the porosity, is 0. So it's not the case in these two-phase flows that the divergence of the individual velocity, fluid velocity, solid velocity is 0. It's the mean velocity taken in this way that is 0. And the other equation, this equation, essentially tells you how the porosity evolves in response to this compaction. So maybe let me just duplicate these equations over here because I'm going to refer to them again. Oh, one other thing. I often find it convenient to write that mean velocity in a slightly different way, which is just to bring these bits together and write it as divergence of phi Vf minus Vs. This will turn out to be the Darcy flux, telling you about the separation of the two phases, and that's the solid velocity. You can look at it as sums of Darcy flux and solid velocity, but that divergence should be 0. So we've got ds phi dt equals 1 minus phi divergence of Vs, that's associated with compaction. There's a melting term, if you want it, and the divergence of the mean velocity has to be 0. 1 minus phi Vs equals 0. Okay, so that's conservation of mass, and that's fairly uncontroversial. Let's turn then to conservation of momentum. So you make an assumption when you're looking at conservation of momentum. Essentially, we're looking at these very, very viscous flows. We're looking at low Reynolds number flows, and we're going to neglect inertia. so the forces are always going to be in balance. If you do that, your statements of conservation of momentum for the two phases written down here, first here for the fluid phase, and then here for the solid phase, look like this. So if you had a single phase system, you would be used to, say, divergence of stress tensor plus density times g equals naught as your conservation momentum equation. Here you've got to write down one for each phase, and you've got to take account of the porosity. So it's divergence of phi times the stress tensor in the fluid plus phi rho f times g, that's the gravity vector, equals, now it equals here an f. So the interesting thing about the two-phase flows is that the two phases can do work on one another, and that's what's captured in the way I've written it here in terms of this, I suppose, interphase force term here. So much the way we had melting telling us about how the melting rates coupling the two mass conservation equations together, here I've got an interface force term coupling the two momentum equations together. The two phases can do work on each other. Now, here I've just assumed, so this just, I suppose, so Newton's third law equal and opposite. Now, in reality, there's really a kind of third thermodynamic bit of the system involved here, and that's the interface between the two phases themselves. And really, and I think Dave's going to talk more about this when he does his talk, we can also think about each of the phases doing work on the interface between the two phases. And that's not captured really in this. This is just assuming that the solid does work on the liquid and liquid does work back on the solid. There's nothing about doing work on the interface associated with, say, surface energy effects. I think our later speakers are going to come to that. Okay, so for now we've got those equations as our conservation momentum. Given these stress tensors, we can define mechanical pressures. I'm just going to define them in the usual way as minus a third the trace of the fluid stress tensor, minus a third the trace of the solid stress tensor. Okay, so we've got two pressures here associated with these two stress tensors here. Okay, I can do a usual decomposition and talk about that stress tensor in terms of an isotropic bit associated with those pressures and a trace-free bit, which I'll write as tau f. So it's just convenient to label it like this. Okay, so that's just a standard decomposition of the stress tensor, which will be useful. Again, I'm going to write these in a kind of asymmetric way. I prefer to have, say, in this case, I'm going to write just one equation for the fluid and one equation for the mean. So all that's doing is I can just I'll leave that equation like that, and I'll just add this equation to this. That'll cancel the f off, give me an equation for the total momentum balance for the two-phase mixture, a mean that just says the divergence of some effective mean stress tensor plus some mean density times g has to be equal to naught. And this is just the fluid one as before. And I'll take my means in exactly the same way in this porosity weighting kind of form. Okay, you'll see why it's sensible to do this in a moment. Right, here's where we start getting phenomenological. Right. Now, you need to close these equations by stating what is the law that describes how these two phases interact. And this is where things get trickier. The equations that, say, Dan McKenzie wrote down in 1984 effectively have an interface force term like this. Now, I mean, there are rules as to what you can write down in terms of these interface force terms. And I suppose the simplest kind of rule that you can think of is that you want to do it, I suppose, in tensor terms in things which are frame invariant. So that tells you, for example, that I can write down an interface force term in terms of, say, the difference in velocities between two phases, but I couldn't write an interface force term down just the fluid velocity, because that wouldn't be a frame invariant choice of tensor quantity to do. But there's a whole host of different things one can think of, and you can look in the work by Drew to see the kind of things one can think of. The simplest kind of choice that gives you the basic physics that you want is just to include these two terms. Maybe the first one is the most obvious that you'd want to include in your interface force term, and that just says that there's some interface force term associated with the difference in velocities between two phases. That's associated essentially with the viscous drag of moving one phase past another. And so you can see how you'd want to have that for some, you can see physically why one might want a term that looks like this. And I'm just going to say this D is some drag coefficient associated with that. So there's some resistance to flowing the two fluids past each other. The second term is perhaps less obvious, but you run into problems if you don't have it. The gradient of phi is one of these frame indifferent quantities, and if you had something with the gradient of phi, certainly dimensionally the thing in front of it must be some kind of pressure. And there needs to be some kind of pressure term associated between the two phases, because I mean, if you think about simplest case of what gives rise to I mean, Archimedean upthrust and buoyancy, it's the pressure acting on the interface between two phases. And you need some kind of force term like that. And indeed, I mean, Dan's main motivation for this kind of term is that it comes up with Darcy's law.
Capillary forces or not?
What, sorry?
Not capillary forces?
No, I think I'm not going to do surface energy in this. I think Sash and Dave are going to introduce capillarity in their talks. Yes, I'm going to neglect those. But there's another pressure here. So I've deliberately not written it as PF or PS. I've just written it as a capital P. So I know dimensionally it has to be a pressure. But the question is then, how does that pressure relate to the other pressures that I've talked about already? Okay, let me run with that force law. Now, to recover the kind of equations that Dan Mackenzie came up with in 1984, you've got to make some choices about how this pressure here relates to those mechanical pressures I've already talked about, this PF and PS. And you also need to write down some equations, some constitutive laws for, I suppose, the trace-free bits of the stress tensor. The simplest ones to do the trace-free bits of the stress tensor. The simplest thing to do is just assume it's like a Newtonian viscous fluid, and say that the solid stress should be related to the I suppose the trace-free bit of the strain rate with some constant proportionality, and I suppose that should be the viscosity. Here I've written it as an eta phi over 1 minus phi to be compatible with Dan. Eta phi here essentially will be about the shear viscosity of the two-phase aggregate. You'll see this when I sum the equations together. Now here you note that for torr F I've written that torr F is 0. The reason that's done, really I could write again some kind of fluid velocity times the trace-free bit of the strain rate for the fluid problem. There is an assumption inherent in when you set up these equations in that the two phases have very different viscosities, many orders of magnitude different viscosities, maybe 20 orders of magnitude different viscosities. So effectively the fluid appears inviscid. So the simplest thing to do is just to set that to 0. So say that the fluid viscosity term is small. Those ones are not too controversial. Then you're left with what to do about the relationships between the pressures. And this is where I suppose you come to what is driving compaction. And the way Dan set it up, essentially, I mean, he talks about it actually in terms of single pressure. What drives compaction is the pressure differences between the two phases cause the matrix to compact. And that's really captured by this one. So really, this is the way Dan formulates in terms of an effective bulk viscosity of the two-phase medium. So write it as zeta phi. Again, zeta phi over 1 minus phi. This just scaling is for convenience. to say that it's pressure differences between the two phases which allow me to compact and expel melt. I've had to make another assumption here, and that assumption here is this P that I had in here, I'm going to say is the fluid pressure. Now, you can develop these equations in a kind of slightly more rigorous way, and Dave Berkovici's done this, by having a look kind of more generally at what laws you can have here, and trying to do it in a way that you keep the symmetry between the two phases. You can think about this P as some weighted average of the fluid and the solid pressure, and think about how that weighting should change. I'm just going to stick with this now, and Dave may or may not say more about it in his talk. So you've made some choices here, so I've been phenomenological. If I make these choices, and what are you going to say?
I was just going to ask, I mean, it's quite clear in the shear stress that you've made a viscous assumption about both phases. Is there any assumption that the two phases are viscous when you make the interface, when you write the interface force down in that way?
What, in terms of just choosing a P grad phi?
The difference in the two velocities. I mean, if I had a dry granular media, for example, would I have a different interface force? Maybe this is a question for later.
I don't know. Sorry.
There is definitely not an assumption about viscosity in
yeah, I mean, the viscosity assumptions coming.
It's just as you say, it's just relative motion.
Yeah, there's only I mean that's what allows you to write that down. But it's this question of the pressures, and that's about the surface energy partition. What, sorry?
Also not in the second term.
In the second term, there's
no assumption about viscosity.
Yes, there's no assumption about viscosity to write a term like that. It's the question about what laws you do here. Yeah.
That second term took me forever to figure out where that came from, but it comes out of if you do volume averaging, the average stress over the interface. Okay, what it really should look like is the stress in each phase dotted with the gradient of the porosity. But if you assume the liquid is inviscid, then the stress on one side is only the pressure, the fluid pressure. On the other side, because they're equal and opposite, you can just leave that in there.
Right. Like
So there is a slight assumption about
the viscosity when you make that the fluid pressure.
Yes.
Yeah. So
that is
it comes into again this
exactly.
rather than writing that down. It's in writing that.
But going back to Jerome's question, though, in terms of if you're looking into granular media or some other sort of media, the first term is really the frictional force at the interface between the two phases. So probably one of the modifications could come by variations in the coefficient d there, which would portray the physics of whatever
Yes.
is going on.
Yes,
Because there will be still a segregation between the phases in that kind of situation.
Yes, I haven't yet said how
He's not a constant.
D is not a constant. And I'm going to talk about how D is defined in a moment. But yes, you're right. Granular media, that would be different.
If both of the phases could support deviatoric normal stresses, then it wouldn't just be P grad phi, as Mark says. You'd need,
Yeah, it would be P, but that P would be related to the other pressures in a different way. That's the.
No, you'd need
Not-
a stress tensor dotted with.
Oh, okay. Oh, all right.
It is.
Okay. Yeah.
So
So
there's
yes, sorry.
this assumption there.
Yes, that's okay. Yeah, there's an isotropic kind of assumption. Yeah. So you could have some general tensor dotted with the gradient. Yeah. Any more? We'll move on because this is the tricky bit. Yeah.
No elastic character to the solid?
I mean, that's a subtle point. Yes. I mean, really. Yeah. I mean, I'm just going to assume it's viscous for the purpose of this. Yes. Doing a poro-visco-elastic would be interesting. For some people can do it. I'm sure it's been done.
Yeah, you change it's that last equation.
Yeah.
Change what you believe is constituted.
In
Yeah,
elastic
make a
media,
Maxwell.
you will have essentially the same interface force. Elasticity doesn't add, it doesn't change.
It doesn't change this. It just changes at this point.
Yes.
Here you
I'll show a little of that, and you're going to show a lot. So.
go. Yeah. Okay. I prefer to write these in terms of means again. So write it in terms of, I mean, you can look at this again. This is this assumption about this P being the fluid pressure. The difference between capital P and the mean. This again, phi weighted pressure. given by this bulk viscosity term. And then, yes, the mean deviatoric stress tensor associated with this effective shear viscosity of the two-phase medium. Once you've got that, you have equations to play with. So if I just take this expression for the interface force, put it on the right-hand side of the fluid momentum equation, then I just want to rearrange this equation. And the nice thing about this minus P by phi, if you choose it to be the fluid pressures, it essentially cancels out one of the terms you get on the left-hand side when you expand here, and gives you the kind of nice form that we get this equation, which is Darcy's law. So you get an expression. Essentially, all I want to do is move that over to there. You get a cancelling of one of the terms, rearrange it. You get this expression for this separation flux, this Darcy flux, porosity times the difference in velocities between the two phases is minus phi squared over d, this drag coefficient, times the difference in the pressure gradient and the rho f g. So this is just Darcy's law, and it's Darcy's law. You can see it is if you choose this d to be a particular form, and yeah, this is what Sasha was referring to. Depending on what physics you think about this, how you choose this d. If you choose this d particularly to be the fluid viscosity phi squared over k phi, then you recover Darcy's law exactly, so that the relative separation between the two phases is controlled by this k phi. This is effective permeability over a fluid viscosity times the difference in pressure gradients from the, I suppose, magma static. So that is describing this percolation process, and it all required that particular choice in the interface force law to get that to drop out. Okay, but that's the kind of physics we'd expect the thing to be. This percolation process is described by this. So we have this equation here left for the total momentum equation, and we have essentially these laws, which one could put in to tell you what the constitutive law for this effective stress tensor for the two phases is. So what we've got here, that's the fluid momentum equation, that's the total momentum equation, and this, if you like, is a constitutive law for the two-phase aggregate in terms of this P, which is this fluid pressure or interface pressure. There's a shear viscosity, and there's a bulk viscosity term associated with this compaction process. So that's my conservation momentum. Maybe I'll make sure I have a copy somewhere by writing it down here. So we've got Darcy's law, pi Vf minus Vs is k phi over mu, the gradient of pressure minus rho fg. We've got some conservation, some expression for the total momentum, balance, and then some constitutive law, if you like, for the mean. Sorry. Minus P I, some identity tensor, plus some shear viscosity term, grad V, plus grad Vs transposed, plus zeta minus 2/3 zeta div V I. Okay, so we've got mass, we've got momentum, as Dan wrote down in 84. We've still got to say things about how these various tensors come about. You've got to talk about, you've got to talk now about, these things with subscript phi I've put on because I'm saying that they could nominally depend on porosity and should depend on porosity. You've got to express some laws for how the permeability depends on the porosity. Normally you look at some law where it goes to porosity to some power n, usually 2 or 3. You've got to express some law for how the shear viscosity depends on porosity, and also particularly how the bulk viscosity depends on porosity. And here it's often assumed that as the porosity gets smaller and smaller, it gets harder to compact, and that you should want some law which goes, for example, like 1 on phi. Now, I think Mark's going to talk maybe a bit more about this in his talk which follows. Okay, we've got some equations for momentum. Let me talk very briefly about conservation laws for energy. So the conservation laws for energy are here. So you've got to write down, yeah, I mean, it's the same, it's another conservation law. We've got to write down here, I've got the internal energy of the system, say UF for the fluid, and US for the internal energy of the solid. We're going to have some average, and it's the divergence, so rate of change with time of the stuff plus divergence of flux of stuff. That's the usual bit of a conservation law. I'm going to say that this thing essentially, in terms of its energy losses, I'm going to think in terms of we can lose, so there could be work, so if I think of a control volume and I'm wondering about the energy budget for that control volume, there's changes due to the work done by tractions at the surface. That's essentially what's captured in this term, phi sigma f dot the fluid velocity plus 1 minus pi sigma s dot the solid velocity. That's describing the tractions at the surface. You can have work done by body forces, in particular here we've been talking about work done by gravity. That's what this term captures. And we could lose heat, and usually captured, again this is a choice of phenomenological law really, some effective Fourier's law for how we could lose heat from the body by conduction. So that's a statement of conservation of energy, and it can be simplified because we've got expressions for essentially the divergence of phi sigma f and the divergence of 1 minus phi sigma f from our momentum equation. So it's usually simplified by using the momentum equation to get perhaps more familiar equations like these ones. So I've just used the momentum equation here. So this is again the same kind of rate of change of time of stuff plus divergence of flux of stuff, heat loss. If I use the momentum equation, this term, there's a term which looks like minus p div v bar. That's a natural term to have in there. And this term here, psi, which is the viscous dissipation, or well, I suppose there's several terms to this. If I was doing a single phase fluid, I'd essentially, so there's 3 terms to this psi. If I had a single phase fluid, I would essentially just have a term like that, and that would be the viscous dissipation associated with shear. If you've got this multi-phase system, you've got these 2 extra terms that appear on the right-hand side of the energy equation. One is associated with this viscous dissipation due to Darcy drag between the 2 phases, and that's this term here, and another one associated with the compaction process, with this effective bulk viscosity term here. So the energy equation really looks very similar to the single phase system. You've just got these couple of extra terms. Actually, writing this viscous dissipation actually gives you another way of actually deriving the momentum budget, and that's actually to start from this notion of a viscous dissipation and to work from the variational principle. You can derive the equation saying it's something which minimizes this particular function subject to the constraint that the total mass is conserved. And then that interface pressure comes out as the Lagrange multiplier, essentially enforcing that constraint. So there are different ways of getting at it, but you could start from this if you thought that was any more natural. Right. Okay, so that's energy. And here I'm going to come to another one of these thorny aspects of the theory that confuses me, and if anyone could help my confusion, I'd be very grateful. You can write the equations for the energy equation in many different ways. You can write it in terms of different potentials. You can write it in terms of enthalpy, or you can write it in entropy, or whatever you like. Here I've rewritten it in terms of enthalpy, and I've said that the specific enthalpy of each phase is the internal energy of each phase plus essentially PV. This is pressure over the density in this phase. Now, I've done something here in that I've chosen a particular pressure. So now there's a thorny aspect in these theories as to what you should choose for the thermodynamic pressure in this system. So, I mean, I feel it should be right that when you write down these equations in terms of thermodynamics, there should just be one kind of pressure that the system knows about. And I think it should be right that you define all your thermodynamic potentials in terms of this pressure that the the two phases know about, and I think it seems a natural thing to choose this interface pressure P. But I might be wrong. It makes the equations rather convenient if you do this, but I don't know a good justification for what you do here. I mean, you could think of, should I use the pressure in each of the phases? How should I, I mean, what should I do? I mean, there's lots of pressures knocking around in this problem. This seems natural, but I don't know if it's right. So if anyone could help clarify. Yeah.
You're suggesting implicitly that you can choose anything for pressure or anything. You still have a choice for pressure, but you don't, because you only get those equations on the board if P is equal to PF.
That's right.
So P is PF. What is the
But there's
choice
still a
to make?
PS that's different from PF,
Okay, so
which
you
is
could
different
say
by the divergence of VS. So I could put PS here.
Yeah, but it's only a conservative potential if the P involved is conservative. In other words, but the difference between PS and PF, if you're assuming that it's this bulk viscosity effect, is non-conservative, so it can't go into an internal energy. All it can do is be dissipated. So if you're going to choose one of the pressures that's excluding the dissipated part, then what you have, it must be right.
Yeah, I mean, that's the argument Dan makes in 84.
Oh, good. Must be right.
But Dan since argued that it should be the solid pressure in jolly mechanics. Where is Dan? He's not. Oh, he's not here. Oh.
I'll show you a simple case that makes it even more confusing. So.
Anyway, I think this is a conversation perhaps we should continue offline. I think this is subtle.
Just for clarification, what is I?
I just mean, sorry, for each phase. So sorry, I've used a notation. So I'm going to write H sub F equals UF plus P over rho F, and H sub S equals UF plus P over rho S. So one of these for each phase. That's what I mean. Instead of writing two equations, just make my life easier. Okay, and you can if you make these choices, you can then carry on. Then you've got an equation, say for enthalpy. If you want to work with that, it's good for say constant pressure situations. More useful often is to think about entropy. So you can write, instead of enthalpy, you can write things in terms of entropy, where the balance looks like this. Here's the viscous dissipation term. Or indeed, often you want to write things in terms of temperature, in which case you care about various derivatives of entropy with respect to T and P. It's where these things like rho Cp, alpha, and things come from. And this all just looks like the same as for a single phase fluid. Now it's just, the only difference is you've got loads of bars for averaging. This term is slightly more subtle. I've just put it as minus gamma times the latent heat. That's a bit more subtle depending on the multi-component system. I've made some assumption about the different components. But essentially that's the kind of familiar energy equation one gets. Okay, so I'm going too slowly, I think. What I should just say, and that's what Paul said, is this isn't closed yet, just having these conservation laws. You need to have some additional closures to finish these equations off. They either come from statements of thermodynamic equilibrium, typically some statement of a phase diagram, or, if you like, some description of the kinetics. And that will close then these set of equations. I think Rich will talk a bit more about what you do in his talk. Okay, so let me just end by just talking about some of the basic then physics that comes out of these equations. So I'm going to forget the energy equation. I'm just going to think of some isothermal problems, no melting. We just have this conservation of mass and momentum for the two-phase system. Okay, so that's these set of equations there. They're over there. A convenient simplification to do is, if you look at these equations here, I've got, this is why I wrote this equation for the mean like this. I've got some Darcy's law here, which I'm going to substitute into this equation here to get rid of one of the equations. So I've got this equation here for the that's now my conservation of mass for the two-phase system, and it's written with this minus divergence of k phi over mu grad p term over here, and there's a body force term over here, k phi over mu rho f g, divergence of it. So I can eliminate this Darcy flux, and now I've got a problem here, which is just for the pressure and the solid velocity. It's a useful thing. So this really then separates into two separate bits. So if you're doing a computational problem to solve this, you've really got two separate bits at this point. I've got this problem here, which is a problem for, say, given the porosity, find the pressure and the velocity, solid velocity, and this problem here, which tells me how to take the porosity forward in time. So it's very much like a convection code. You have one equation, which is the Stokes equation, tells you, say, given temperature, what the velocity field is, and then you can use, say, the conservation of energy equation, the equation for temperature, to step temperature forward in time. You've got that same kind of flavor to the equations here. So I'd call this one, so this is the time-stepping equation, and then I've got this, what I'll just call a Stokes-like problem, and this is the one coupling Stokes and Darcy. Now what I want to talk about is first the basic physics of this set of equation now, this Stokes-like one. So we need some boundary conditions for the problem, and there's different choices of boundary conditions one can make. One can either talk about setting tractions or velocities or some kind of mixture. I'll highlight the difference between these and the Stokes equations here. So in the Stokes equations, you would say, if I just had Stokes equations for a single solid phase, then I would be talking about setting this traction here, sigma s dot n, or the velocity here. I would never talk about setting, say, the pressure. That's different in this set of equations here, and it's different because of this term, and this is the term that leads to the interesting extra physics here, in that you've got two derivatives, essentially, of the pressure, and that essentially means you need an extra boundary condition. And it's that's natural. If I just had the fluid phase on its own, if I just had percolation, essentially what I would have is some kind of Laplace or Poisson equation for the pressure, and that would need boundary conditions on the pressure or the derivative of the pressure. So here we've got both, so I need to have some boundary conditions on tractions for both the solid and the fluid. And because of this assumption of an emissive fluid, it just becomes either just talking about the pressure or the normal derivative of the Darcy flux. So I need to have some combination of conditions from that. So here's what I've got. So I could write using Darcy's law just to point out that this really is a condition on the derivative of the pressure. So I can either have pressure or derivative of pressure, normal derivative of pressure, tractions or velocities. And for example, one could have a rigid impermeable what, sorry?
What is your boundary? I'm somewhat confused.
At the moment, I'm just saying there are different boundary conditions one could apply on a system.
There is no boundary between two phases. Yeah.
I'm not talking about, so I could have some domain with a boundary on it, with a two-phase global boundary condition. I'm talking about global boundary conditions, and that they can be of this type.
It might be worth mentioning that it's really the boundary between a one-phase system and a two-phase system as well. Because, you know, if you have an internal boundary where on one side you have pure solid, and on the other side you have solid plus liquid, then you'd have to.
Yeah, I mean, you'll have some condition that represents that, but I mean, you could have two-phase mediums each side and talk about the continuity of these kind of things. Let me give you some specific boundaries. I'll look at a specific problem. Maybe this will make it clear as to what kind of things I'll be thinking of. I'm running rapidly out of time now. Let's have a look. Yes, so for example, one could think of like a rigid impermeable boundary. So one could have a boundary where one is pushing on the solid and allowing melt to escape. So like a coffee plunger or something like that, where one presses on the solid phase and the fluid allowed. Sorry, that's the second one of these, a free flux boundary, where one pushes on the solid phase and allows melt to escape freely. Or one can have an impermeable boundary where you don't move the solid, can't get any fluid out. They're just examples of boundaries one could have. So let me introduce quickly the compaction length. These equations have a natural length scale within them, and if I set the right-hand side of these equations to 0, forget the body forces, and just look at the various terms in the equations and just do a simple kind of scaling argument. saying that if these terms are all to be in balance, say there's, if I take, so this is just the equations without any body forces on the right hand side. So if I just say there's some natural pressure scale, if this term is to balance this, where there's variations on some length scale delta, just say k phi p over mu, I'll do the div grads of some delta squared. It's got a scale with some v over delta and a similar effective expression for this. P over delta has got a scale eta v over delta. You can solve these equations and just say that, okay, there's a natural length scale being defined just by the equations themselves, and this natural length scale is of the form permeability, some viscosity to do with the solid over some fluid viscosity. That just naturally comes out from the equations themselves, and this is effectively the compaction length. Now, it's usually defined in this way, where we define the compaction length as k phi. This particular combination of the bulk viscosity and shear viscosity is eta plus 4/3 eta over the fluid viscosity mu, defined in this way because essentially motivated by the one-dimensional problem of compaction. What I've got up here is just a one-dimensional version of those equations where I assume constant properties. If I were to scale these, the natural way of scaling them is on this particular combination, because this particular combination comes out the total momentum equation. And in a scaled form, the equations look very simple indeed. They're just some very simple ODEs that one can solve. They've got these exponentially growing and decaying solutions. And if I look at the kind of simplest problem, and this is this, I suppose, coffee press problem I was talking about. So if I've got some half space, one-dimensional half space, filled with this two-phase medium, and I push it at one of the ends where I push it, so I push on the solid and allow the fluid to flow freely, then what happens is that you get compaction happening near where you're pushing it, and the length scale over which that compaction happens is controlled by this compaction length. That's where that scale comes into the equations. So if I take these equations and solve them, I get these exponentially, essentially decaying solutions. So if this thing here, dv s dz, I'll talk about as the compaction rate. Okay. Now, the real question you've got to ask yourself in a lot of this physics is whether the compaction length is small or large compared to the things in the problem that you're interested in. You get different styles of behavior depending on whether the compaction length is small or large. Now, so there's usually another length scale in your problem, and you can ask yourself, how does the compaction length relate to that other length scale in your problem? And what you can do in the kind of simplest, naivest form is go back to the equations and think about the balance when I've got another length scale in the problem, and it won't in general be the case that both of these I can get kind of similar order of magnitudes from all of the terms. In effect, you can end up neglecting one of the terms, being large or small compared to the others. Now, there's two kind of main limits here. The simplest one is actually if you assume that the compaction length is large compared to whatever kind of length scale in your problem you're thinking about. So I'm thinking of a layer of a particular thickness, I'm thinking about compaction length large compared with that layer, or if there's some obstacle in the flow, or that, I'm thinking the compaction length being large compared with that obstacle. If you've got equations like that, then essentially this term is effectively small and can be dropped, and you get a consistent problem where I just solve this equation here, divergence of Tor bar, I make an approximation, that's roughly 0. That is just an equation on its own for the velocity with those velocity boundary conditions. In fact, it's the Navier-Cauchy equation of elastostatics. And in that approximation, all the velocities and compaction rate are just governed by the properties of the matrix. I can then, once I've solved for the velocities, I can know the compaction rate, I can solve this problem, this essentially Poisson problem for the pressures. And I've got some boundary conditions for the pressures. So that's one limit of the equations that I get if I assume the compaction length's large. So everything's then just governed by the properties of the matrix. If if the compaction length's small, well, I'm going to be a bit rough and ready here. Really, this term in some sense is negligible. But there's subtleties to just dropping this term. This term matters in boundary layers, and essentially it's a singular limit of these equations. I mean, loosely, if I just drop the del squared p term on here, I mean, I'm just saying div v is approximately 0, and I've just got the Stokes equations. But I've kind of lost the boundary condition, and this particular limit is singular, and that limit matters because it's thought that, say, the compaction length probably is small in various of the kind of tectonic scale problems. Now, chopping it off completely is not quite right. It controls a lot of the interesting physics, and it controls the behavior of boundary layers. I mean, I can return to that kind of simple 1D problem if I just look at compaction within a layer where I've got two boundaries here. So I've got my one boundary, which is this kind of coffee plunger one where I push on one phase and allow stuff to escape, and I have another boundary which is impermeable. So if I look just compaction between, so I've got a plunger moving up here, I've got an impermeable boundary here. Okay, I can go and solve these equations in terms of shines and coshes. It's just matching boundary conditions. And you can see the two kinds of different physics you get depending on whether, in this case, I've got an epsilon parameter here. Tell me how the kind of length scale of my layer relates to the compaction length. If the compaction length is large, then essentially what I can do is chop out that term, and I'm just solving essentially d squared vs dz squared equals 0, just gives me a linear velocity, and a compaction rate, say the derivative of this, which is uniform. The other way, I fall into trouble if I have a small compaction length. What I'd like to do is neglect that term, but that would just tell me velocity is constant, and I wouldn't be able to match the boundary conditions. So it's a singular limit, and it's one you've got to be careful with. I know I'm rapidly running out of time here, so I want to make sure I do the things that Mark needs for his talk.
Got most of them.
Well, sorry, I've got most of it. I think I do need. You do need this one.
Well,
oh, you've got a
a
sign.
version of it anyway.
Right.
I'm
Okay.
use those ones per se. So.
All right. So I've just talked about the 1D thing. You've got different. What matters is the ratio of your compaction length to the scale in question. Obviously, the interesting questions are not just 1D. They're in 2D and 3D. And there's a very nice decomposition of these equations that you can make that separates out the different bits of the problem, the compacting bit from essentially from the shear deformation. And that's these are the momentum equations where what I've done is I've assumed all the properties are constant. I've written an equation here for the compaction rate. What I'm going to choose is this C, the compaction rate, and this one here, the vorticity. If you take, say, for example, the curl of this second equation, curl grad is 0, curl grad is 0, you get curl of, well, you get curl of Vs, or curl of the vorticity is 0. And since the divergence of the vorticity is 0, you get the nice result, and familiar from Stokes' flow, that the vorticity is harmonic. If you play with divergences of the equation, take the divergence of this term, you get 0. Divergence here, you'd have del squared p, you'd have del squared div vs, but I know del squared p up here, so it relates this div vs to this del squared of div vs, so it's this one here for minus del squared of the compaction length, so compaction rate plus compaction rate is 0. And this is the bit that's about the compaction. So there's this Helmholtz-like equation, or Helmholtz with a positive definite Helmholtz style equation for the compaction rate. Now, what you can do is, and this is what Mark did, is a nice way of writing this is in terms of splitting it up into potentials, the gradient of a scalar potential and curl of a vector potential. Then you can write this as essentially a biharmonic equation for a vector potential, and you can write this compaction rate here and then a Laplace thing for the compaction rate. And what's nice about this is you can use lots of standard methods then for solving these equations. So in these, if you assume all the properties are constant, there's lots of very standard methods you can use to get nice analytic solutions out for this. I think, yeah, I mean, one thing I was going to talk very briefly on is, here's just an example. This is just shear past a sphere, just to show you the difference between large and small compaction length. Just focus on this. This is just analytical solutions for shear past the sphere. Here's the compaction rate in a situation with a large compaction length, where the length scale over which the compaction takes place is controlled by the size of the object. If the compaction length is small, you're constrained to doing everything in these compacting boundary layers. Okay. So I'm gonna skip over the melting columns, I'm afraid. I don't have time for that. Sorry, Ian. Just to highlight some of the things that I still find confusing in this, and I would like some help on. This question that came up about pressures and the relationships between pressures still bugs me. For numerics and various things, it's important to worry about these singular limits in this issue of having, I mean, we're often close to a limit where we have small compaction lengths. And in fact, for example, we might have zero porosity regions where we might have zero compaction lengths to worry about. And there's a singular limit there. Responsible boundary layer behavior and how you treat that in numerical models is an interesting question, a difficult question. I'm often worried about situations, say, where porosity gets large. This is all very much predicated on there just essentially being a small fraction of melt where it can percolate along grain boundaries. How do we deal with those situations essentially where it becomes more like a suspension, disaggregates? That may be important for modeling some of the experiments. And how do we kind of blend between small porosity behavior and large porosity behavior? A general thing is about how to be less phenomenological. It's putting some of these things on a more formal basis, and maybe that requires going to grain scale physics. This is the same question that Paul raised. I am interested in some of these kinetics, especially since the two phases aren't in equilibrium when they get to the surface. And I apologize for overrunning, Mark. I really do. Okay, I think I should stop there. Thanks very much.
Take some questions for our setup.
Yeah, is there any questions while Mark's setting up?
No.
No. Mark can answer all the difficult questions now.
Yeah, right.